You can never actually see anything enter a black hole. Imagine launching your worst enemy in a spaceship toward one. As they get closer, you'd expect them to speed up, right? Instead, they slow down and freeze. Not metaphorically, literally frozen in time. What's going on here? Einstein's math has the answer. This is not science fiction. This is the bizarre yet beautifully consistent reality predicted by Einstein's general theory of relativity, the most accurate theory of gravity we've ever had. And the deeper you go into the math, the stranger the universe becomes. Black holes that trap light, white holes that spew it back out, and wormholes that connect entire universes. But the real magic? It all starts with math. Let's take a walk through Einstein's equations and see where they lead us. But be warned, once you cross the event horizon of curiosity, there's no going back. Let's go back to your nemesis in the spaceship. As they fall toward the black hole, the force of gravity intensifies. You'd expect them to accelerate, but something strange happens. From your point of view, their motion slows. They seem to freeze at the edge of the event horizon, the invisible boundary surrounding the black hole. Their hand, once shaking a fist at you, begins to slow down and eventually stops. Not because they've given up, but because time itself is slowing down for them in your frame of reference. Their image dims, reddens, and then disappears. This isn't a visual trick. It's relativity in action. To grasp the strangeness of black holes, you first need to understand the genius of Einstein's insight. Before him, gravity was thought of as a force, an invisible hand reaching across space. Newton imagined the sun pulling on Earth the way a magnet might tug at a nail. But even Newton himself admitted he didn't know how that force worked across empty space. Then came Einstein, who asked a radical question: what if gravity isn't a force at all? What if it's just the shape of the universe? Einstein proposed that space and time aren't separate things. They're part of a single connected entity called space-time. And massive objects like the Earth, Sun, or black holes don't send out invisible forces. Instead, they bend the very fabric of space-time around them. Other objects, including you, me, or even light, simply follow the curves of that fabric. Imagine space-time as a giant, stretchy trampoline. If you place a bowling ball in the middle, it creates a dip. Now roll a marble nearby, and it spirals inward, not because the bowling ball is pulling it, but because the surface it's on has been curved. This is what Einstein's field equations describe. On one side, they tell you how matter and energy are spread out in the universe. On the other side, they calculate how space-time must bend and warp in response. In his own words, matter tells space how to curve, and curved space tells matter how to move. That's not just poetic, it's profoundly accurate. From the orbit of planets to the behavior of galaxies, Einstein's math has been tested again and again, and it keeps holding up. But the deeper you dive into those equations, the stranger space-time becomes. And that's where black holes enter the story. Einstein couldn't find an exact solution to his own equations at first, but someone else could. Carl Schwarzschild, a physicist working on the front lines of World War I. In a muddy trench under the thunder of artillery fire, he found the first real solution. He imagined a perfectly spherical mass in otherwise empty space, a simplified model. And from that, he discovered something no one had predicted: black holes. The math described a space-time that got infinitely curved at a specific radius, now called the Schwarzschild radius. That's the point where the escape velocity equals the speed of light. Beyond that, nothing, not even light, can get out. The math also showed something weird. Space-time breaks at this radius. A singularity. But was this a real physical boundary? Or a mistake in the coordinates? Think about a map of the Earth. It's a projection of a round planet onto a flat surface, which introduces distortions. Some maps stretch countries near the poles. Others squish them near the equator. In the same way, we create maps of 4D curved spacetime, and our coordinate choices can distort reality. Schwarzschild's solution showed a singularity at the event horizon, but later physicists realized this was just a coordinate artifact. With the right transformation, that singularity vanishes. It turns out nothing special happens at the event horizon for someone falling in. From their point of view, they cross it without noticing. Time doesn't freeze. The universe doesn't end. They just keep falling until they reach the real singularity at the center. To understand what's possible near a black hole, physicists use something called a Penrose diagram, a simplified map of space-time where time runs upward and space runs sideways. In these diagrams, light rays always travel at 45-degree angles, which helps us visualize the limits of movement and causality. Every moment of your life is surrounded by a light cone, a region showing everything that can affect you, your past, and everything you can still affect, your future. Outside a black hole, this cone is wide open. You can send and receive signals, move in different directions, and choose where to go next. But once you cross the event horizon, everything changes. Your future light cone tilts inward. No matter what you do, every path forward leads to one place, the singularity. Escape becomes impossible. Now here's the twist. When physicists extend these diagrams using Einstein's equations, another region appears, one that nothing can enter, but things can come out of. It's the opposite of a black hole, a white hole. In theory, it expels matter and energy, but never takes anything in. It's bizarre, but it's also what the math demands. White holes are hypothetical regions where matter and energy are ejected, but nothing can enter. They're like time-reversed black holes, and the math doesn't stop there. When you fully extend Schwarzschild's solution, you find that the black hole connects two universes. The structure becomes a wormhole, a tunnel through space-time. Enter one end, exit somewhere else, maybe even in a different universe. But there's a catch. These wormholes are unstable. They collapse before anything can get through. They're like bridges that vanish as you try to cross them. Still, the math allows for them. Now what if the black hole is spinning? After all stars spin, so black holes should too. Solving Einstein's equations for a rotating mass took decades. But in 1963, Roy Kerr cracked the code. The solution revealed an entirely different beast, a ring-shaped singularity instead of a point. Two horizons, an outer one you can't escape, and an inner one where strange things happen. A region called the ergosphere, where space itself is dragged along with the black hole's spin. In theory, you could enter the inner horizon, avoid the singularity, and emerge somewhere else. A white hole, a new universe, a loop of universes connected through rotating black holes. But reality is crueler than math. While Einstein's equations allow for things like white holes, wormholes, and connections to parallel universes, there's a catch. The math assumes eternal black holes, ones that have existed forever in a completely empty universe. But real black holes form when massive stars collapse. That means they start existing at a specific moment in time in a universe filled with matter and radiation, not a vacuum. It gets more complicated with rotating black holes. The math says they could contain wormholes and even multiple universes inside. But there's a problem. Light and energy can build up along the inner horizon, like traffic piling up on a one-lane bridge. Over time, this pileup becomes so intense that it creates its own singularity, which would destroy the wormhole before anything could pass through it. Physicists have also explored traversable wormholes, shortcuts through space that you could walk or fly through. But to keep them open, you'd need a strange form of matter with negative energy. According to everything we know, that kind of matter shouldn't exist. So, while the math opens some wild doors, nature might keep them closed. Then again, people once said black holes were impossible, and now we've photographed one. Einstein's equations started with a simple idea. Gravity isn't a force, it's geometry. But when you follow that math, it opens doors to some of the most mind-bending possibilities in the universe. Black holes that trap time, white holes that spit it back, wormholes to other worlds, universes within universes. Maybe they're real, maybe not. But here's the real question. If general relativity predicts all this with such elegance, what else might the universe be hiding? just waiting for us to do the math. What if black holes could actually store information and even teleport it somewhere else? Click the next video to explore the weird link between black holes, quantum mechanics, and the fate of all knowledge in the universe.